this. Take a look. NASA scientists say it's a comet. That's what they say. They've named it the 3-1 Atlas interstellar object.
It's a supposed comet is catching the attention of some of the nation's most renowned scientists.
We've got some fresh images of 3I Atlas, a third ever interstellar object observed from Earth, currently racing through our solar system.
Just after midnight, silence unfurled itself across observatories in Chile, Hawaii, and beyond. Screens flickered, telescopes realigned themselves, and for a brief moment, the vastness of the cosmos pressed down with an eerie urgency rarely felt in the steady routine of scientific research. Comet 3I/ATLAS, the third bona fide interstellar object ever detected transiting our solar system, had swept into view. But from the start, this was no ordinary astral wanderer. On July 1st, 2025, the Asteroid Terrestrial Impact Last Alert System, or ATLAS, an automated astronomical survey system with sites including the peaks of northern Chile, picked up a remarkable streak, a comet breaking through the dusk boundaries of our solar system. At first, the world paid little attention. Comets, asteroids, and other minor bodies routinely cross the night sky and are commonly charted by astronomers, most met by fleeting curiosity, and then returned to the backdrop of stellar routine. Yet 3I/ATLAS was different. Data began to trickle in. What had initially seemed an unremarkable event grew with each discovery. NASA's TESS observatory, the Transiting Exoplanet Survey satellite, revealed that 3I/ATLAS had already significantly brightened before its official discovery, with images capturing the object as early as May 7th, 2025. The comet's unusual glow was documented even before ground-based telescopes were aware to follow its passage, beating the headlines into the scientific record. This unusual detection timeline drew the attention of astronomers and science institutions worldwide. What distinguished this comet? Its brightness, unexpected pre-discovery visibility, and undeniable interstellar path all combined to create a rumble of interest. Media, theorists, and government policymakers quickly took notice, driving a surge of international attention and prompting what commentators dubbed the media tsunami of 3I/ATLAS. Two calls from Washington, D.C. reportedly reached astronomers at nearly the same moment, evidence of the rapid spike in high-level interest. Even for scientists familiar with the limelight of big discoveries, the sheer speed and scale of response were unprecedented. Yet amid media speculation, one question persisted. What was behind this early brightening? And how could it tell us more about the origins and makeup of this visitor from another star? The approach of the unknown. As the northern summer advanced, international teams pivoted their attention to this unusual object. Though the first Atlas sighting, in July 2025, started the official record, TESS's May image proved 3I/Atlas was not just an ordinary comet slowly emerging from the dark. It had grown unexpectedly bright before standard observation techniques picked it up. Two distinct periods of observation, beginning in May and intensifying through June, helped establish the comet's trajectory. Unlike solar system comets, which typically brighten in a predictable arc as they near the sun, 3I/ATLAS seemed to begin its energetic display unusually early. Not only was its interstellar origin a rarity, but its optical outburst before significant solar warming contradicted the expectations set by decades of prior observations of inbound visitors. This early display prompted hypotheses about its composition. Was the nucleus abundant in exceptionally volatile materials, or had it accumulated rare ices over eons spent in the emptiness between stars, ready to sublimate at even modest warmth or radiation? Alternatively, did something about its outer crust make it especially reactive? Though the science is evolving, much of what made 3I/ATLAS unusual could plausibly be attributed to its long interstellar journey and unfamiliar chemistry, not to anomalous signals or unmeasured physical effects. The comet's behavior, though strikingly out of step with normal comets, did not present evidence of extraordinary processes beyond established chemistry and physics. Instead, it offered a vivid example of how little we understand about the diversity of objects traveling the galaxy between stars. Before we continue, make sure to subscribe to the channel so you don't miss more updates on the strange visitors that challenge everything we think we know about the cosmos. Now, let's move on. Unusual observations in the early light. As is often the case in major discoveries, the most important data arrived before most were prepared to notice it. TESS, though not designed primarily to observe comets, caught evidence of 3I/ATLAS's outburst in early May 2025, providing scientists with a view of the object before it was identified by Earth-based observatories. Was this early burst a transmission in any literal sense? No radio signals or communications in the common meaning of the word were detected. Instead, the transmission in question was the comet's unexpected photometric activity, its physics speaking to us in the language of light curves and spectroscopic signatures. Astronomers scrutinized the available TESS data for patterns and clues that could reveal the origins and composition of this rare visitor. As the weeks went by, it became apparent that the comet's activity was not uniform. Rather than following the usual crescendo of outgassing and luminosity as it neared perihelion, 3I/ATLAS seemed to dim even as it approached the Sun. Observatories worldwide shifted focus, coordinating observations to trace its mass loss and chart its evolving spectrum. But the explanations remained embedded in known physics. Unfamiliar volatiles in the nucleus, altered structure from its journey, and the effects of solar wind and radiation on interstellar snowballs were all examined. A particularly noteworthy observation took place on August 6, 2025, when the James Webb Space Telescope trained its near-infrared spectrograph on 3I/ATLAS. Webb's advanced instrumentation allowed scientists to analyze the comet's chemical makeup and energy output with greater precision than ever before for an object of its kind. These readings marked a shift. Rather than any new outburst, the comet's spectrum indicated a less active, more subdued phase had begun, contradicting some of the most optimistic predictions for perihelion fireworks. While the early excitement led some to speculate about signals or hidden messages, the real message delivered by 3I/ATLAS was a lesson in the variability and unpredictability of interstellar objects as they interact with solar radiation. Perihelion and the solar encounter. Every comet's journey around the Sun is expected to reach its climax at perihelion, the closest point in its orbit to our star, when sunlight typically triggers maximum outgassing and visible activity. 3I/ATLAS's path would bring it to its closest approach, about 1.4 astronomical units, approximately 130 million miles or 210 million kilometers from the Sun, around October 30th, 2025. In most cases, this is when comets provide their brightest and most spectacular displays. Yet the curious timeline of 3I/ATLAS meant that by the time it passed perihelion, its previously intense activity had already faded. The anticipated surge in visible brightness simply did not occur. Instead, observers saw a comet whose most energetic phase was already past, its mass loss and visible activity growing ever fainter as it rounded the sun. For the scientific community, this was both a surprise and an opportunity. Why would an interstellar comet peak so early and fall quiet at the solar climax? Were its volatile compounds spent? Or did solar heating expose a more durable, less reactive core beneath the surface? Theories continue to be refined, but the principal lesson remains clear. Interstellar objects challenge our intuition, and each new arrival upends established patterns. A chorus of curiosity. The public fascination with 3I/ATLAS was fueled not just by its scientific rarity, but also by the speed and scale of media coverage. The media tsunami referenced by observers was a real phenomenon. Few recent discoveries have drawn such intense, coordinated attention from both the public and governments. The calls from Washington, D.C., which reached astronomers at a pivotal moment, reflected the heightened interest in near-Earth and unusual cosmic phenomena, but also the recognition that interstellar comets offer crucial scientific opportunities. As questions spread, was the object dangerous? Could it bring new insights into the birthplaces of planets? International coordination and information sharing redoubled. Amateur astronomers joined professionals in scanning the skies, uploading images, and collaborating in unprecedented ways. In real time, orbital parameters, early spectra, and brightness measurements became public knowledge, driving not just scientific progress, but also a global curiosity and a small renaissance in amateur astronomy. For educators, students, and laypeople, 3I/ATLAS provided a unique chance to witness scientific discovery in action. Real-time simulations, online sky maps, and digital classroom events let people around the world follow the comet's journey as if participating in the process themselves. The real message of an interstellar arrival. What then did the world learn from 3I/ATLAS? At its core, this object was a time capsule, a fragmentary witness to processes far beyond our own planetary formation. With only 3 confirmed interstellar objects identified so far, Oumuamua in 2017, Borisov in 2019, and 3I/ATLAS in 2025, each carries precious evidence about conditions in star systems light years away. Although no transmission in the sense of a signal or message from intelligence was detected, 3I/ATLAS's sudden brightening, strange evolution, and relative silence near Perihelion offered astronomers a laboratory in motion. Each spectroscopic reading and photometric curve holds clues about outgassing, about primordial ices and dust, about how interstellar travel may shape and change small icy worlds over millions of years. This is the true message of 3I/ATLAS as science currently understands it. An opportunity, fleeting and unique, to refine what we know about cosmic chemistry and the mechanics of objects born far from our sun. If this comet's history was written elsewhere, in a cold, ancient belt circling an uncharted star, it stands now as a rare testament to the variety and resilience of raw material found between the stars. Return before sunrise. After its closest approach in late October 2025, 3I/ATLAS left the inner solar system. Not in a blaze of light as frequently hoped, but in a soft, steady dimming. According to predictive models, it will become visible again just before sunrise in November 2025. a subtle glow on the horizon, most likely limited to early morning hours and increasingly faint as days pass. Its receding tail, visible only to keen sky watchers, represents less a triumphant finale than a quiet recapitulation of its enigmatic arrival. For professionals who spent months chasing every update, each fragment of new data, this understated end was in some ways as telling as the comet's initial burst. Rather than providing spectacular, prolonged observation after perihelion, 3I/ATLAS's activity fell beneath the threshold of easy measurement. This aligns with what is emerging as a pattern among interstellar objects. They may behave differently, peaking in activity well before entering full sunlight. James Webb's Spectral Insights. The contribution of the James Webb Space Telescope on August 6, 2025, deserves particular mention. Using the near-infrared spectrograph, Webb's readings allowed for a careful inspection of the comet's outgassed material, the building blocks shed as the nucleus warmed. The spectral data did not support wild speculation of exotic physics or entirely unknown compounds, but did supply a wealth of detail about the ratio of normal cometary materials to more volatile and rare components. If anything, the relative absence of pronounced late-stage outgassing helped support emerging theories about what makes interstellar comets distinct. The loss of volatile compounds may be accelerated and uneven, shaped by their exposure to deep space. In addition, repeated cosmic radiation and micrometeor impacts might seal outer crusts, meaning most preparatory outburst occurs prior to perihelion, leaving little reactive material for solar heating to ignite later. This sequence of observations reframed what astronomers look for in future interstellar detections. Instead of predicting traditional patterns, researchers will now remain alert for abrupt, early brightening episodes that quickly subside. The saga of 3I/ATLAS is a record of both discovery and missed opportunity. That TESS imaged the object in May, and that ground-based teams confirmed it only with more pronounced activity weeks later, illustrates the challenge of capturing fast-moving, unpredictable phenomena. Data is stitched together from disparate sources: space-based telescopes, all-sky survey images, spectral readings, and citizen science reports. For many, this is a sobering reality. The window for transformative observation of interstellar visitors can be narrow and nearly impossible to forecast. Each part of the electromagnetic spectrum offers another chance for insight, but only if researchers are ready to seize it as soon as it appears. While no sense of alien communication or exotic unknowns was proven, it is these wider lessons about scientific vigilance and the unpredictable nature of cosmic discovery that now define the standing legacy of 3I/ATLAS. Echoes in the night. The passage of 3I/ATLAS, though less spectacular in appearance near the Sun than first anticipated, nonetheless marked a watershed moment for astronomy. International scientific coordination, significant media and public attention, and the unprecedented use of space-based instruments created a living case study for future interstellar comet research. If 3I/ATLAS transmitted anything, it was simply evidence, a prime example of how dynamic and unfamiliar the workings of our universe remain. Each outburst and quiet phase, each brightening and fade, is a single phrase in the ongoing narrative of cosmic change and persistent mystery. Scientists gained valuable data on how to recognize, characterize, and rapidly coordinate the study of similar objects in the future. For the lay public, the episode was a call to curiosity. a reminder that the universe's rarest guests may arrive quietly, offer only the briefest opportunity for direct study, and then slip away, leaving more questions than answers. As 3I/ATLAS dims and recedes, its lessons are clear. It reminds all who observe the sky, professional and amateur alike, that the universe operates on its own schedule, and discovery often comes down to timing and preparation. The hidden transmission was not a coded message or anomaly, but a metaphor for the hidden stories revealed through patient observation, careful analysis, and international collaboration. In the coming years, more interstellar objects will pass through our solar system. Some will announce themselves clearly, others will remain faint whispers. The tools and lessons honed during the scrutiny of 3I/ATLAS will equip scientists so that less will be missed in the future. As the dawn breaks and the comet moves on, what remains is the certainty that every watchful observer is part of this unfolding cosmic dialogue, one that spans generations, continents, and the space between stars. If you have shared in the sense of wonder sparked by 3I/ATLAS, a world not of our sun, but of the vast unknown, consider following along with new discoveries as we chase the universe's next mystery, one fleeting visitor at a time.